My name is Matt Johnson. I'm the CEO of QCWare. Thanks very much to the organizers for allowing me to address this topic, which I think is something that everyone in the room cares about. So I'm going to be talking about quantum machine learning, quantum artificial intelligence, and specifically the path from where we are now to finally getting to enterprise deployments and what's kind of between here and there. So very clearly, if you look at the popular press, in particular, all of the quantum hardware vendors have been talking about this being one of the killer application areas, and that includes, again, Google, D-Wave, IBM, Rigetti, Microsoft. The question really is, it's really twofold. Well, what do they actually mean by AI in particular? And then what does quantum processing do to improve the performance of that? So there are three questions that enterprises are going to ask. The first one is, why is quantum processing even necessary? So if you are a machine learning practitioner who is completely agnostic about the classical computing resources, so algorithms and hardware that you're using, the question is, where are the problems, the ostensible problems that can be addressed by that? That's the first question. The second question is something we've talked about for a while. Full-scale, error-corrected quantum processors and large-scale quantum annealers won't be available for some time. So the real trick to get a deployment in the medium term is to find a way to exploit the power of these non-error corrected and smaller scale annealers and put them into a machine learning workflow in an enterprise. And then the third question is, okay, assuming that all theoretically works, how do you implement quantum processing resources into the workflows that these enterprises have? So let's very, very quickly, to make sure we all have a common understanding of artificial intelligence and machine learning, I just want to go through what most people believe is the correct delineation between these areas. So if we start with machine learning, we would define machine learning methods as those where you're using data, existing data, to make predictions about the future. And that includes the canonical forms of machine learning which we've depicted here. This is different from artificial intelligence, where you have a method where you are using information you're collecting about your environment to enable you to get smarter about what to do within that environment. So just like a human being, an infant learns about its environment by sensing it, this is what this form of intelligence is doing. And of course, these are machines and not humans, so it is artificial intelligence. So I think all of that we all have an agreement on. So let's look at various use cases here, all of which I'm going to be talking about have the potential, and I think it's fairly well validated, have the potential to be accelerated by quantum processing, the potential. So first of all, in the artificial intelligence camp, you have a Roomba vacuum cleaner that's exploring a space, a room, to learn about it. It doesn't have training data that's teaching it about the room. It's learning as it's doing. A typical unsupervised learning case is you're reading Google News or some similar service from another vendor, and there's this behind the curtain, this clustering that's going on that is gathering together news articles that have some perceived likeness and feeding that into your news feed, as opposed to a supervised learning example like a Netflix rating system, where in this case the data is actually labeled, the label in this case being the rating that users have given to a particular film, and based on those labels or ratings, you're getting recommendations about which films you should be watching. Now, all of these have the potential to be accelerated by quantum processing, but when things get really interesting is in these real-world cases where, and this is in most of the cases for artificial intelligence and machine learning, you're incorporating multiple types of machine learning and AI in order to provision a service. So in this case, with Watson, Siri, or Google Now, that service is actually partially a trained algorithmic approach and partially a true AI approach. There's a lot of computational complexity there, and it's precisely there in computational complexity where quantum processing has the potential to accelerate. Likewise, if we look at a Google AlphaGo example, clearly this is a game, but it doesn't take a lot of imagination to imagine real-world use cases where, again, the logic or the knowledge built up in AlphaGo can be used for real-world applications. And again, there's a lot of computational complexity around that. So now that we've defined that, let's take a look at what we want to talk about in answering our first question, which is, where are we starting to push the limits? Where do enterprises care about getting more performance? So forget for a moment about these enumerated lists below them, the technicalities. In simplest form, enterprises that are provisioning these services care about the speed, power consumption, and accuracy. So on the speed side, of course, there are two elements to that. There's the training time, which can take hours and days, and then there's the inference time, which should take milliseconds. On the power side, the interesting promise of quantum computing is that, as opposed to the case of data centers with classical computing hardware, where power consumption kind of scales at sort of this kind of a curve with the computing resources that are being deployed, quantum processing has the potential to have a much shallower curve where the increase in power consumption doesn't have as steep of a curve as you do with classical. So actually, hardware vendors are looking very careful at this. It's unclear how big of an advantage it can be, but it looks like it could be an extremely significant power and cooling energy savings. And then finally, accuracy. Very simply, if you could enter a text search in a search box and only get one hit, and that hit is the right answer, that's obviously a lot better than needing to comb through hundreds and thousands and millions of hits to get the right answer. So what we've done is looked at, for each of those three factors that contribute to the performance of machine learning workflows, what specifically at a level of technical abstraction needs to be addressed in order to get those improvements. And clearly, we have tried to map each of those, I guess, 11 items into speed, power, or accuracy, and it just doesn't work. But at the very minimum, you can classify these problems into two categories. One, which is purely algorithmic, and hence a quantum algorithm area of research and exploration. And then two, implementation challenges, which is this intertwined hardware and software solution. It is certainly arguable that all of those points can be addressed with quantum processing. The only question is where you're going to see the most improvement in the shortest period of time. So moving on to the next question, which is, where can we possibly see near or medium-term deployments for enterprises of machine learning? What we've done on this slide, and again, forget about a lot of the specific data entries. We simply replicated or simplified the same slides that we showed where we kind of delineated, here's machine learning, here's artificial intelligence, and we've listed all of the known and discovered quantum algorithms and major subroutines that have been discovered and published. And so what this does show is that for the major forms of machine learning and artificial intelligence, there are already known and understood quantum algorithmic solutions to those. The issue is, if you were to compare this list to the equivalent set of algorithms for classical solutions, this is quite small. So when Alan Ho talked about the fact that this is a very nascent field, if you think about the whole universe of classical machine learning algorithms being this large, the set of quantum algorithms that cover off that same problem space is much, much smaller. The only thing, however, that is preventing that whole space being covered off that classical is currently doing is the discovery process. Most of that discovery process now is happening at universities and at research labs, and to a lesser extent in the quantum computing community. But clearly, as the hardware gets closer and closer, there's going to be a ton more investment to add significantly to this list. If we've said, and I think everyone's been quite careful about stating very clearly that there has not yet been a demonstration of an end-to-end speedup of a problem using a quantum algorithm. So that's true. There has not yet been a live data set running on a quantum algorithm that has provable end-to-end speedup. And there's a couple of issues that need to be overcome to get us there. And the first one is something, again, that's been bandied about today in the room, but that is there's been very little work that's been done, first of all, to discover new quantum algorithms, and secondly, to have a ton of work being done in the enterprise community to figure out which problems enterprises have that are most amenable to being solved or accelerated with quantum algorithms. The second point is really interesting, and it has to do with something quite peculiar to quantum processing, which is that in order to process data, the data that's being churned has to be represented in a quantum format. And most of the problems that the machine learning community is solving today is obviously classical data. So that classical data has to be converted into quantum data and then reconverted into classical data. And that conversion and reconversion adds a lot of time. And maybe an extremely oversimplified example of this or an analog to this, and it's very oversimplified, but it might relate. If you're talking on your cell phone to a friend, your friend's communication is coming to you as an analog waveform or signal, and that analog signal gets converted into a digital format, which then is interpreted, you can do something with, and then recast or reconvert it into analog. So that analog to digital conversion and then digital to analog, in a way it's similar to that. Now, clearly in the RF community, that A to D and D to A conversion, that's been beaten up on for 40 years, and there's no latency, there's no problems with that. This field for quantum processing is much newer. One of the interesting approaches, though, as you see, is to try to harness or develop this quantum RAM approach to allow you to get a speedier conversion of your data set into a quantum format. And then finally, I think Jerry Chow and a couple other people talked about, actually almost everyone in the room talked about, what do you think the first applications are going to be that work or that can show some kind of a speed up. It probably is true that data that is natively in a quantum representation and doesn't need to be converted is going to be able to be fed through more speedily. And I should point out that these thoughts are ones that are echoed by Scott Aronson and kind of our extractor from his work. Scott is actually an advisor to our company, and Scott's kind of the intellectual junkyard dog of the quantum computing community. And so I think we're all being very careful about not overstepping claims that are being made here, but if anyone ever does, Scott's kind of the first person to nip at your heels. And so the material here is it's consistent certainly with that, the view espoused by Scott. So coming back very, very briefly to known quantum algorithms that can be used for machine learning, the two that stand out right now, and there's only two, and hopefully by this time in 2 years there'll be 20, 30, or 50 that stand out, are quantum recommendation systems akin to the Netflix problematic that we just described, and then topological data analysis, which in a very oversimplified way can be associated with looking for needles in haystacks. Let's shift gears now very quickly to the third question, which is how do you implement quantum processing into technology stacks? I'm running a bit low on time, so I can't give the example I wanted to on this slide, but effectively if you think about performance issues associated with, in this case, a supervised learning workflow, you have really two classes of temporal problems. One is the days or hours it can take to train dating sets, and that is an area where quantum processing can be applied. And the other is that second phase of the machine learning workflow, which is the inference phase, where a user is querying or working to execute a problem, and that inference stage, the shorter that period is, the better it is for the user. But the objective, of course, is to have that entire cycle be quicker with quantum processing than it is with classical machine learning methods. So QCWare's opinion, and this is strictly our opinion, when we search for these near or medium-term machine learning employments, we're looking at the couple of characteristics that we think are the most important to show, okay, this is where we should start looking. So we kind of create a Venn diagram, both for annealing machines and on the next page for circuit model machines to reflect where we look. So the three areas that matter to us are, first of all, problems that are running slowly, where a user is saying, I need less latency, I need quicker training times. The other one is low dimensional problems. So clearly, with low qubit counts, it's going to be impossible to run a high dimensional problem on these early generation machines. And then the third area, without getting into detail, has to do with the hardware topology that's the problems being run on, and the specific qualities of that topology that do comparatively have some kind of advantage. So it's the intersection, in our minds, of those three sets, which is where we're looking. And so one example of a problem that we've found that's interesting is taking a very large set of data with a limited number of features. And in this case, if you think about large portfolios, very, very large portfolios of mortgages, of bonds, of loans, trying to predict default rates. So that sort of a class of problem is something that we care about. Moving to circuit model machines, it's sort of a similar Venn diagram where the major difference is we have a different type of hardware topology, which in a similar way has some comparative advantage in solving a particular type of problem. So again, when we look at the intersection here, one area that we're looking at is recommendation systems, and not necessarily the consumer-focused recommendations, but ones which may have applications beyond sort of a consumer user community. So very, very quickly, I've only got 2 minutes left. We're talking about implementation. If you look at some of the major cloud service providers who are provisioning machine learning services now, we list them, and we've also listed underneath their kind of logos what we understand to be their one of their hardware options of choice to do machine learning work. We also list below that, let's call it unaffiliated machine learning focused processors, which will find cloud platform providers. In any event, the point of all this is that there is no technical reason why quantum processing can't be implemented into any of those technology stacks. And what we have here is a very, very generalized technology stack for machine learning, where at the hardware layer, we add just about all of the types of processors that are being employed. This is very generalized. And on top of that, libraries, distributed computing frameworks, and all of these other elements that are used to some extent in machine learning workflows using classical hardware. So the question is, how do I integrate quantum hardware? And it looks something like this in a very notional way. So clearly at the hardware level, you're adding, and this is where hybrid approaches are kind of being manifested. You're simply adding to that workflow a QPU, and on top of that, at each of those major layers of the technology stack, you are adding quantum software, quantum algorithms to build up. So the idea is that those users out in the enterprise area, we don't want them to be interrupted one bit. We don't want them to have to learn anything new. We just want the services that are being rendered or the programming that's being done to work just like it does for all these other hardware types. 20 seconds. The only conclusion is what everyone else has said in the quantum computing community. The thing that will advance our understanding of deployments is more contact with enterprises, and QCWare is really looking forward to talking to all of you about how we see these employments working and how we could work with you on it. Thanks a lot. I don't know if you want questions.